When you think of the deadliest diseases, you might imagine terrifying pathogens or the slow, agonizing loss of function in Alzheimer's. But one of medicine's greatest paradoxes is a surprisingly simple gas: oxygen, or more specifically, the lack of it. Hypoxia, the deficiency of oxygen in tissues, is a double-edged sword, driving both destruction and regeneration. In diseases like chronic wounds, stroke, and cancer, hypoxia can tip the balance between life and death. And as we unlock the secrets of this molecular Jekyll and Hyde, we discover how to weaponize its power. In non-healing wounds and ischemic stroke, oxygen deprivation leads to tissue necrosis and functional loss. Yet in cancer, hypoxia fuels tumor aggression, metastasis, and therapy resistance. That's why cancer cells, like those in the deadly core of a tumor, exploit hypoxia to their advantage. As they rapidly divide and outgrow their blood supply, they hijack hypoxia-inducible factors, or HIFs, which promote survival and trigger the formation of new blood vessels to keep them alive. This dark adaptability makes hypoxic tumors the ultimate therapeutic challenge. But what if we could turn the tables? By understanding how hypoxia drives tumor growth, we might be able to starve aggressive cancers by cutting off their oxygen supply. For NASA, hypoxia isn't just a disease mechanism, it's an existential threat. Space travel exposes astronauts to microgravity-induced vascular dysfunction, increasing risks of ischemic injury and impaired wound healing. Could engineering organisms with enhanced tolerance to hypoxia help us survive journeys into deep space? A recent study found that by tweaking the genes of a nematode, they could double its lifespan and improve survival under low oxygen conditions. These hardy survivors could hold clues to hypoxia-tolerant human adaptation. But there's another approach. What if we could engineer materials that generate oxygen? One solution is to create synthetic, photosynthesis-inspired scaffolds that continuously produce oxygen. This could be a game-changer for Mars missions where medical evacuation is impossible. Imagine a bioengineered patch that astronauts could apply to their wounds, reducing the risk of infection and impaired healing. These oxygen-generating materials aren't just science fiction. Researchers have developed compounds like calcium peroxide that can release oxygen slowly, potentially sustaining cells until host vasculature takes over. But critics warn that these materials could pose a hazard if they release oxygen uncontrollably, potentially fueling oxidative damage or even cancer growth. As we stand on the cusp of a new medical revolution, hypoxia emerges as both a villain and a tool. For NASA, conquering hypoxia could mean survival beyond Earth. For bioprinting, oxygen-generating materials might be the key to lab-grown organs. But as we manipulate the delicate balance of oxygen, we must tread carefully. Will we control hypoxia, or will it control us? Only time will tell.